So hello everyone, my name is Raghav and in this video we will solve this problem. So in this problem what it says is that we have to find the first index in this array, like we will be given an array, and in the array we have to find the first index for which the sum of the elements on the left is equal to the sum of the elements on the right. Here it is given that find the first index in the array such that the sum of the elements before it is equal to the sum of the elements after it. And in case if there is no element in this array, the given array, if there is no element such that the sum of on the left is equal to sum on the right, we have to return -1. Okay, so talking about the brute force approach, what you can say is that we will iterate over this array. So for finding the sum on the left, what you will do is iterate over this array, and for every index we will find the sum of the elements on the left and find the sum of the elements on the right. The current index, we are just talking about finding the sum of elements on the left, so it is I minus 1. And the first loop we had been talking about is I is equal to 0 to I is equal to n minus 1, considering that the size of the array is n. And for finding the suffix for each element, you will iterate from j is equal to I plus 1 to j is equal to n minus 1. And in this manner, we will find the sum of the prefix and find the sum of the suffix, and then we can just compare it. Let's say the sum of the prefix is equal to left, or you can say that the sum of the elements on the left is equal to left, and the sum of the elements on the right is equal to right. So now you will just compare that if left and right are equal, in case we don't just return I plus any 1 index, then we will just return -1. Okay. So what is going to be the time complexity? By the way, this is the brute force approach, the most basic one. Here TC, time complexity, is equal to big of n square, because for each element we have been finding the sum on the left and sum on the right, which is itself taking big of n, and we have been iterating over n arrays, so it's gonna be big of n square. And we are not requiring any extra space, like it's just constant, so that's why the space complexity is big of 1, that is constant space complexity. And let's say if this would run or not. So in the problem, n can be as large as 10 raised to the power 6, which means that if you try to run this code, the brute force, then it will fail, because 10 raised to the power 6, if that can be the value of n, then n square will go to 10 raised to the power 12, which will definitely fail. So we have to optimize it. So how can we optimize it? I hope you have heard about something known as pre-computation or prefix sum, suffix sum. That's what we will use. So for finding, I'm not gonna be explaining prefix sum and suffix sum here. In case if you are not familiar with it, then you can just search about this on internet. You can just go to YouTube and search about it, prefix sum and suffix sum. Like prefix sum is enough. You will know what suffix sum by itself, and you can search about it in case if you are not familiar with it. I'm just directly gonna be telling about it, what you can do. So in this problem, like in this solution, for optimizing it, what you can say is just create an array with name t of n size, and here we will like this is gonna be an int array, and we will iterate over this array once and find the sum of the elements till that index in this array. For example, it's gonna be something like this pre-array is gonna be something like 1, 4, 9, 11 and 13. And if you carefully look at this array, then the sum of the first one element is 1, the sum of the first two elements is 4, the sum of the first three elements is 9, the sum of the first four elements is 11, and the sum of the first five elements is 13. In the similar manner, you will create a suffix array. And by the way, for initializing this prefix sum array in this manner, so that you will have the sum of the first I elements at pre I, it will take big of n. And after doing this big of n, we are not gonna be nesting it. After completely finding this, we will find for suffix array, so it will tell me about the sum of the elements on the right and the current element. So it's gonna be 2, 4, 9, 12 and 13. If you carefully look at this array now, the sum of the last element is 2, the sum of the last two elements is 4, the sum of the last last three elements is 9, and the sum of the last four elements is 12, the sum of the last five elements is 13. It has been storing in this manner. And now what you can do is just iterate over, like just iterate for I is equal to 0 to I is equal to n minus 1, and now you know that this element contains the sum of the elements on the left and current element, and this one contains the sum of the elements on the right and the current element. So if you compare both of these, it is like this range and this range, right? So like this one is common in both of them, so it doesn't matter if you subtract this from both of them or not. You can directly compare these two. Since these two are not equal, so we'll go ahead and let me write it properly. So these two are not equal, these two are not equal, and now these two are equal. So it means that the sum of the elements on the left and sum of the elements on the right will be true for this index. This is I is equal to 2. So we will return, like this is the third element if we start counting this first element as index 1, so it is going to be third index. That's why we will return I plus 1. Now the time complexity, now the new time complexity is big of n. Why is it big of n? Because the first loop we had, um, because the first loop we implemented was was taking time complexity of big of n. Then after that we took another loop for big O of n. Then after that we took another loop for big O of n. So approximately the time complexity is big O of n, and the space complexity is gonna be big O of n because we created two arrays of size big O of n. So the space complexity is approximately equal to big O of n, and this one would actually run if you try to submit the solution with this approach, then it would pass, but we have to optimize it even further. Now the more optimized solution, for the more optimal solution, what you can see is that for the first element, if you had this as the sum on the left, like these as the left elements and these as the right elements, right? When you come to this index, you don't necessarily need to calculate the sum from the beginning, and for this you don't necessarily need to calculate the sum from the end till here. What you can do is just add this element to the left and remove this element from the right? But you can just do this, that let me show you it once again. Once you checked the elements on the left and elements on the right for the first index, and you realize that these two are not equal, so when you come to the next element, what you can do is add this element to the left. So the add this element to the left sum. So if the left sum was initially 0, now it would become 1, and it is actually covering this range. The new range is this, and you can remove this current element from the this range for the right elements, or you might call it a suffix. So you just need to remove this one now. So you can do it something like this. Right was initially equal to 12 and now it is equal to 9. है And now after this we again see that left and right are not equal, so you need to check for the next element. When you come to the next element, what you can do is add this one to the left range and remove this one from the right range. Now right would equal to 4 because we removed 5 from it, and the left one would look become 4 because we added 3 here, right? And now we can see that left and right are equal, so this is the element for which the sum on the left and sum on the right are equal. That's why we will return 3. That is I is equal to 2 here, and we will return I plus 1. So what is the time complexity here? Here you can see that we have been just iterating over the array once. Like for the first time you calculated the value of right, the calculated the sum of these elements. So it took you big of n, and after that you just iterated over the array once, and it took time complexity of big of n. So the time complexity is big of n, which we actually achieved without it as well. But now the good part is that the space complexity is big of 1. We are just taking like constant extra space. So for the first approach, what you can do is iterate over the array once. I'm writing the brute force approach right now, and for all of the iterations, you will find the sum on the left. So sum equal to left, and iterate on the left range. So that is j is equal to 1, j is equal to 0 till j is less than I, j plus 1, and add all those elements to left, and then find the sum on the right. And then we will just compare if left and right are equal or not. So we will say that if left equal to right, in that case return I plus 1. Otherwise, like if you iterate over all the elements and you still don't find anywhere where left and right are equal, then just return minus 1. So if you try to submit, I won't submit it. If you just try to compile it, then it would be compiled. So we have to optimize it. The way we will optimize it by using prefix and suffix sum. So let's say we have an array with name tree of size n and another array with size n with name suffix. For the first element of prefix, it is itself equal to the first element of the array, and afterwards I can find the sum of the other elements in pre-array by just iterating over the by just using one loop. So pri is equal to p of I minus 1 plus a of I, and then I can do the same for the suffix array. Let's say here like this, and here I can say that suf of n minus 1 is equal to a of n minus 1, and I will iterate over the array once. I is equal to n minus 2, I is, and now we will just iterate over the array once and see if there exists an element for which prefix is equal to suffix. So we will say that if tree of I equal to suff of I, then return I plus 1. And in case if there is no index for which prefix and suffix are equal, then we will return minus 1. By the way, in this problem, AI can be as huge as 10 raised to the power 8, and there can be 10 raised to the power 6 elements. So it is possible that the sum of these elements might exceed the range of integers. So it's safe to take long. Okay. I didn't tell about this in the brute force approach, though you have to use long in that as well. And now let's come to the optimal one, the optimal approach. Here we will have two variables, prefix and suffix. At the beginning, tree is 0, or let's take left and right. So left is equal to 0 and right is also equal to 0. We will calculate the sum of the elements on the right first. So just iterate over the array take this as well. And after that, we will iterate over the array once again, and this time we will keep removing elements from the right and keep adding elements on the left, so that we have to iterate only once. Here we will remove the element, remove the current element from the right range, and then you will check if left equal to right or not. If they are equal, then just return I plus 1. And now remove, like we have already removed the current element from the right, and we will add it to the left, so that when I is implemented for the next index, the current index is gonna be included in the left one. And in case if this doesn't come true for any of the indices, that left is equal to right doesn't come for any of the indices, then in that case we will return -1. And let's try to run this code, and let's try to submit this as well. So yeah, it passed all of the test cases, and it like that's the most optimal approach. In this, we are having big O of n time complexity and big O of 1 space complexities.